Okay, video number 5. In this video, we're going to be studying light again. This time around, we're going to hit concave mirrors. We're going to try to do an example that will help you with the problem set. So let's begin by reviewing some things that we talked about last time. Last time, we learned two formulas. One formula dealt with what a focal point is on a mirror. If you continue out the curvature of the mirror, you will eventually make a circle. If you take the radius of that circle and half it, you will have the location of where light can be concentrated when it comes in parallel. We came up with some rules. We called them ray rules. These work for any kind of thing, lens or mirrors. It's about how you come in and how you leave. If you come in parallel, you leave based on the focal. If you come in based on the focal, you have to leave parallel. If you come in at the origin, you must leave at an equal angle. So we're going to build on those ray rules, and we're going to build on that formula for the radius of the curvature here. So what I'm going to do is I'm going to use some graph paper, and I'm going to go through and do an example of what happens when you have an object in front of a concave mirror. So let's begin by drawing in a y-axis. So I'm going to put the y-axis kind of in the middle. And then I'm going to show kind of the curvature of the mirror by curling up the ends like this. Then I'm going to show that it's a reflective surface by putting these little lines on, which lets everyone know that we're dealing with a mirrored surface here. I'm going to go to about the middle of the mirror, and I'm going to draw in an x-axis. It looks to be about the middle. And then each one of these dots is going to correspond to a centimeter. Each one of these boxes, sorry, not dots. And I'm going to put an object, and I'm going to put it in front of this concave mirror. Let's say that this concave mirror has a focal length. So there's going to be a number of things that I'm going to give you. Okay, so I'll kind of keep track of those up there. So the focal length, on the problem set, it's 8. But here, I'm going to use 5. So that'll be the focal length on this. So if light comes in, it'll be directed 5 away. So I'm going to count over 1, 2, 3, 4, 5. I'm going to label it F for focal. 5 boxes, 5 centimeters. Then we're going to put an object behind the focal. So let's label this, and we'll say D sub O for distance to object. I'm going to place the distance of the object, let's say we put it at 8. So here I had 5, 6, 7, 8. And this will be the location of my object. Now I'm going to make this object, let's say, 3 tall. So it's going to be 3 boxes tall. Now the thing we use to represent an object is an arrow. So it looks something like this. Okay, so we have the object, we have the focal length, we have the curvature of the mirror. The reflective side of a mirror is called the positive side, and the negative side of the mirror is on the non-reflective side. This is also called the real side, and this is called the virtual side. So what we're going to do then is we're going to apply, oh, by the way, the radius of the curvature of this would be equal to 10 using this formula right here. Okay, so if the focal is 8 and you put 8 in for F and you multiply by 2, you would get 16. So that's one of the blanks on the problem set, so I thought I'd mention that. All right, so now we're going to apply these ray rules here. So I have my ray rules, come in and leave. So let's apply them. Come in parallel, easy enough. You take a ruler, you line it up. This represents like light would be coming in and reflecting off of this, or this could be a candle producing light. And the ray has to travel in a straight line, and so it does, and it comes over and it hits the mirror. So it comes in parallel, and then I want to turn my ruler so I'm lining up where it intersected with the mirror, and then take it straight down through what we call our focal point. So we do something like that. And then we're going to do the exact opposite now. So I'm going to try to keep the same color code going here. So I'm going to use this color right here that I used before. And we're going to come in through the focal. So I'm going to take my ruler and I'm going to line it up, and I'm going to come in based on the focal, and then I'm going to leave parallel. So then I turn my ruler so that it's parallel to the x-axis, and that gives me a good idea of how I'm going to depart. I just straight on out. So I kept my rules, right? And it gives me a pretty good idea of where it's going to form. But I can confirm this with our last ray rule. And my last ray rule says I have to go in from the top of the arrow through the origin. So I'm going to do that here, come in. And then I'm going to leave at an equal angle. Well, how do you make sure you have an equal angle? Do I get out a protractor or something? No, we don't want to do that. We just count down 1, 2, 3, 4. So we would kind of come down like this and then just keep on going. So you would get something that looks kind of like that. And you can see my ray rules aren't really intersecting all that well. In fact, they're not intersecting well at all. And I think that I made an error. So ignore that one. And then we'll come back here and I'll redo it the right way. I counted down 4 when I meant to count down 3. Don't be like me. All right, so then we come down and we leave. There we go. That's much better. So see how our rays are all intersecting right here? That's what you want. You want them all to intersect because that's going to give you an idea of where the image is going to form. So my image is forming right about here, just like this. So I'll label it I for image. So we had our object, we have our image, and we can go through and we can come up with some things here. So based on my graph that I just produced, I can come up with the following things. I can come up with how far away the image is forming. We'll call that DI. To do that, you count your boxes. If this was 5 and this is 8, 9, 10, 11, about 11 and a half is what I'm getting. And it's on the positive side of the mirror, so it's positive 11 and a half. Okay, that's one thing we'll always have to find is how far away is the image. Another thing is how tall is the image. So we'll call it the height of the image. Now notice that this arrowhead is pointing down. That means it has a negative height. So if we count our boxes, I would count 1, 2, 3, 4, about -4. And this doesn't have to be perfect, okay? This is an approximation here. We use our ray tracings to come up with an approximation, and that's what we're getting here. And then last but not least, magnification. Now magnification, like on binoculars or prescriptions for your glasses, are always expressed as a multiplier. So don't think like we're solving for x here, it's just times whatever. And if the number is bigger than 1, that means it's enlarged, and if the number is less than 1, that means it's reduced. What we do to figure this out is we just want to compare our heights. So if I compare these two numbers here, -4 and 3, it can give me an approximation for what this would be. So I could say times -4 thirds. If I take that down to a number, that would be 1 1/3 or 1.33, and it's a negative value. So that would be my magnification. So how do you know if you're right or not? Like, how do you know if you did a good job or not? Well, that's where math is going to come into play. So yes, we are going to do these same numbers that we just came up with, but we're going to do it mathematically. So building on all this stuff now, our ray rules, our ray diagramming, and now we're going to learn how to solve using formulas. Right? It's physics after all. So the first formula we're going to use is called the Lensmaker's equation. 1/f equals 1/di plus 1/do. And so we can use this relationship to solve for things like, in this case, di, distance to the image. So my focal length is 5. So if I say 1/5 equals 1/di plus 1/do, which was given. So that was 8. Notice I'm taking these things from this post-it note, which are things that will be given to you. These are answers that we're going to be trying to come up with, but we can't trust these because these answers came from the graph. What we got to do is we got to get the answers, but we got to get them from math so they're exact. And hopefully these will match up a little bit. So we got to do a little fraction work here, so hang on. So we're going to put in 1/5 equals 1/di plus 1/8. And now we're going to kind of replace di and solve for it by coming up with a common denominator. So what's a common denominator between 5 and 8? Well, you're probably thinking, how about 40? Yeah, why not? So we're going to do 8 40ths and 5 40ths. And then we're going to say 1 over di. So what we got to do then is we got to subtract this number from the other side. So we come over here and we subtract, and we get 3 40ths equals 1 over di. So therefore di, when we flip it, would be 40 thirds. And 40 thirds, better get our friend the calculator. 40 divided by 3 is 13 and a third. Now that's not too far off what I had before. That's not too far off of where we were before, because previously we did it with our graph, we got 11.5. So that's ballpark. That means my graph probably wasn't great. I'm going to trust this math way more than I would want to trust my graph answer. Like if I had to pick one to put in for the quiz, I'm picking 13.3 because I don't want my measuring error to come into play. I mean, good God, look at that scribble line. I would definitely not go with that. All right, so that's the first thing. So that's our first thing. If we're kind of keeping track of our math answers here, which I think I will, DI that we found from math was 13.3. So what comes next? Well, we have another formula that we can use to do this as well, in addition to the Lensmaker's equation. So the other formula is called the magnification equation. Magnification equals the height of the image over the height of the object. But this is one of those equals situations, right? Like it equals this, but it also equals this. So it also equals negative di over do. So we're going to go ahead and we're going to put in some things that we just solved for. Not my graph answers, that's illegal. But this, I can put in numbers like this, and I can solve for things that I need to find. First, though, we got to come up with our magnification. So we do this in a bit different order. Like we're going to find our magnification before we find the height of the image this time. Last time we did DI-HIM. This time we're going to do DI-M-HI. So let's start with HI over HO. And come up with a magnification. Actually, you know what? I lied. We're gonna do this first. Negative di over do. So I'm going to say negative, and I'm going to use my math answer, 13.3, and then I'm going to divide that by the given. These are fair game up here, the yellow paper, 8. So we're going to do this quick little thing that's going to give you my magnification. So calculator time again. So this time around, I'm going to do negative 13.3, and I'm going to divide by 8, and it's going to give me negative 1 2/3. So m was negative 1.67, let's say, 1 2/3. Well, what did we get when we did it? We had negative 1 1/3. Ballpark again, right? Like, not hateful. I'm definitely going to go with the negative 1.67, the math answer, rather than the graph answer, though, when I have to input it for a grade. Last but not least, we're going to use that magnification of times negative 1.67. We're going to say that's the same thing as saying HI over HO. HO was given to us. Height of the object was 3. So we can put that in here, and then we can solve for HI. So it's as simple as taking 3 times the negative number. 3 times negative 1.67 comes out to be a negative 5.01. So basically negative 5. And then let's go back and see what we had for our graph answer. Well, we had negative 4. Once again, I'm not going to trust my graphing. I'm going to go with my math when I'm taking the quiz, and I have to pick which one I want to put in. Now, how would I turn this in, let's say, for the problem set on the quiz? Well, there's going to be a section where you have to take a picture and you have to attach your graph. And there's going to be a section where you have to go through and you have to punch in all your math answers, right? So I've been punching in this and this and this. And then there's also a section where you have to describe what you produced. So I want to talk about that a little bit, the descriptor things. All right, so we are going to talk first of all about whether this is a real or virtual image. Real or virtual? So that's our first question. Real or virtual? A couple ways to tell, all right? One way to tell is if it forms on the real side of the mirror, we say it's real. Another way to do it is to look at your math number and say, oh, it's positive, real. If it was negative, it'd be virtual. If it forms over here on the non-reflective side, it's virtual. It can't be projected. This, we can project the image onto a wall or something like this. If it forms over here, you cannot. That's why it's virtual. The rays never intersect if it's virtual. Okay, not only do we have to decide if it's real or it's virtual, we also have to decide if it's right side up or upside down. So we would say, is it erect or is it inverted? In this case, when we look at our graph, we're like, look, it's pointing down. Therefore, it's inverted. We can also tell because the sign in the math is negative, and we can also tell because the magnification was also negative. So the math gives us two clues. Just the direction of the arrowhead can tell us over here if it's erect or inverted. Last but not least, is it enlarged or is it reduced? So what do we have here? Well, we want to look first at just comparisons of arrows. This one was 3 tall. This is at least 4 tall. So I would say, hey, you're enlarged. I can also kind of make a comparison of height of object to the math answers, and you can see -5 over here is definitely bigger than 3. And last but not least, is the magnification having absolute value that is greater than 1? And yes, it does. Therefore, it's enlarged. If it's a decimal less than 1, then we would say, hey, that's reduced. Okay, so that's how we go through and we describe it. So this particular image that we formed, we would say is real, inverted, and enlarged. And we used another number of formulas to get there. One formula we used to get there was the lens maker's equation. Another formula we used to get there was our magnification equation, right, which is this one right here. And we put that together with the things that we learned previously, like our R equals 2F, and last but not least, our ray rules. So it's already starting to add up a little bit here, right? We're up to all these things now. All right, so I'm going to have to make another one still to talk about what happens when we move the object in front of the focal, because we don't do the same things in the ray trace. So it looks like I got one more video to make after this one. So stay tuned.